In this video, we are going to see one of the last features of an optical block, the lens aberrations. Lens aberrations refer to that one phenomena produced in the optical systems that include lenses in which the light is spread out in some regions of the space instead of to be focused on a point. Such aberrations cause that some part of the image can be seen, appreciated, like blurred or distorted. The exact distortion or type of blurring depend, of course, of the specific aberration, and we have different like chromatic aberration, spherical aberration, coma, field curvature, and distortion. We will review a little bit all of them, starting from the chromatic aberration. This one describes how a lens is unable to focus simultaneously and correctly the different wavelengths that compose the visible light at the same point. So as you can see, it's not only that a lens can have problems in focus the light one point, but also that depends on the specific wavelength that compose that visible light. The spherical aberration is another kind of aberration that consists in that the light rays entering the lens cannot converge precisely in only one point. It's similar to the previous aberration, but in this kind is considering the ray lines with all the across all the wavelengths and not the wavelengths independently. This phenomena is produced because the spherical lens refract less the rays in the center area of the lens than those that are entering in the edges of the lens. Similar to the previous one is the aberration called coma or chromatic aberration. This also is related with those rays, with the rays entering at different points in the lens, but this time we are focused in the fact that the rays can be inclined with a certain slope, as opposed to the previous one that we were considering just a straight rays. So again, the phenomena is the same. Depending on which point the ray is entering, the lens has a variable capacity to refract the light, and sometimes has in the inability, it has a certain limitation in refracting the different rays just at the same point for producing a sharper image. In this case, due to the geometry of the physical event, instead of just producing a circular blurring, the blurring will have another typical shape in the form of teardrop or comet. The field curvature results from the fact that we are projecting light using a lens that is curved, but the projection is onto a flat sensor. So in the same way that it's not possible to cover perfectly without any wrinkles a flat paper over a curved surface, we cannot project perfectly the light from the curved lens into the flat sensor. This can be appreciated because in the edges of the image, those regions can appear more sharp, more blurred, or distorted in comparison with the sharper areas of the center of the image. Another kind of aberration is the distortion. This is produced when the lens is unable to retain the rectilinearity of the incoming rays. This can have the origin of this phenomena can be different, but for example, it's very typical of the very wide angle lenses that can capture a very wide angle. That is the positive part, but the disadvantage is that it introduces important geometric distortion. Specifically, the pin cushion distortion is the one produced when we are using wide angle lens. But there are other phenomena that can produce another kind of distortion, like the mustache distortion or the barrel distortion. Specifically, the barrel distortion was more related to the old technology of cathode tube rays used in the old television and monitors. Well, that's all for regarding the optical aberration. Now we are going to see one of the last elements of the optical block, the optical filter. This device, as filters, their main purpose is to selectively transmit the light of different wavelengths and can be characterized using their frequency response that specify the magnitude and the phase behavior of every frequency component. We have different types of optical filters. Neutral density filter, color filters, color conversion filters. For example, neutral density filters are used just to attenuate the signal amplitude of the incoming rays. With this, you can obtain several interesting effects, like for example, it can be used to acquire one image that is acquiring an image cascade, an image waterfall. If you use no filtering, you can see how the water is frozen in the image. But sometimes you want some kind of effect, of artistic effect, in which you see or you can observe like the water is flowing. It's flowing with foam. You can obtain that using this kind of filters, because this kind of filters reduce the incoming rays. So to correctly excitate the sensor, you need more time, and in that extension of the time that the camera is acquiring the external light, there are some parts that are fixed, the background, and there are other parts that are moving, in this case the water flow, and produce that phenomena like the water is flowing, is with foam, because everything in that part, the light is mixing, is in motion. Other filters are like the color filter, are just used to produce the correct feeling or the correct appearance according to the human vision system. The sensor characteristics, the spectral response characteristics of the sensor, the CMO, the CCD, are different from our human eye. So perhaps we need, or we would like that the image that occurs on one camera have the same appearance as we will see it directly. In order to do this, we need use this kind of filters that alter the behavior, the acquisition frequency response, or the behavior of the sensor to reproduce more like a human being the image. And of course, we have another kind of color conversion filter to produce different effects in the color that can be more artistic, or for emphasize some color in the image, etc.